So thank you all very much for showing up. Thank you so much for coming. I'm really excited to show you all the exciting projects we've been making. So we are Tachyon. I'm Jackson Hoekstra. I'm the chief engineer for our company. And I'd like to go ahead and start by introducing the span and scope of the project. So this is a team. You got more information about each of us in our brochure. We each perform a specific role within Tachyon. We were tasked, along with Pixis, to produce a two-stage orbit, fully reusable vehicle that was capable of human spaceflight and can carry 29,000 kilograms into low Earth orbit. We are going the route of a wing body second stage that lands horizontally, while the other team is doing a vertical landing. Our job is conceptual design. This is a game of cost, risk, and feasibility predictions. We have 4 distinct phases in this conceptual design, and we'll get more into detail about what each of these are and what we did in each of them. But first, here's the schedule. We're currently coming out of configuration layout and about to finish up with configuration evaluation. We'll go in more into detail about that. But first, let's dive right into project initiation. This is where we justify the mission elements and come up with a basically mission profile and challenge the impossible flight phases if there are any, or identify the actual challenges if what each of these are in each flight phase, and do a literature history review of each flight phase, similar vehicles, and similar missions. And ultimately produce a mission trade matrix, which will help us do a quick, rapid analysis of the mission and the vehicle.
Hi everybody, my name is Matthew Laurie. I'm the lead of the trajectory and performance discipline. So we work very closely with synthesis and project initiation in order to define the mission elements and the vehicle expectations for what we want to achieve based on the requirements that we have been given. We do this through a method of very in-depth literature research, where we take the past and the present, we break them down into concepts like functions, roles, missions, and previous performance parameters, and then we break that down even further into data, observations, inferences, and purposes and multidisciplinary implications. So what that results in is the ability of creating the orbital elements, so servicing future commercial space stations at very high inclinations, which we expect them to be at due to the coverage of the Earth, and with the Axiom space station first beginning life at that inclination. From here, we generate trade studies, varying the inclination, increasing and decreasing the payload metrics at the requirements. Next slide. So in order to visualize what that looks like, we have identified 14 different flight phases. Each of those flight phases for each mission has a well-defined speed and altitude and performance. And we delineate that to every other discipline so that they can perform their first initial analysis. Next slide.
So that takes us into the next stage, which is parametric sizing. And this is the phase where we essentially use convergence to size our vehicle before we even know what it looks like.
In Hyper, the sizing methodology we decided to choose was hypersonic convergence. The reason we used that is because it allowed us to use all flight regimes, and it allowed us to use the weight and volume and as a budget. There was many key parameters that we had to identify, so we tasked the teams to identify those key parameters to give us back those parameters.
Hello everyone, my name is Yusuf. I'm the lead of the geometry team. So the geometry team in the parametric sizing phase was tasked with generating a geometric database of past, present, and future vehicles. That way we can decompose the vehicle into first state and second state. And then we can develop a trend line equation that's going to be used in the hypersonic convergence equation. Finally, we can screen the solution space generated by the synthesis team and find what each point looks like in terms of visualizing the vehicle. Next slide, please. So, firstly, we're tasked with verifying our methodology, being the official weighted area from the space shuttle and also the X-20 dinosaur. That way, we can carry on that methodology into more space access vehicles. Next slide, please. Using the criterion of R-squared value greater than 0.9, we were able to iterate through the vehicles that we generated to find the trend line equation necessary for the hypersonic convergence equation. Two formulas here was the accoutrement slenderness parameter, and the KW value. Those values determine how the shape and size of your overall vehicle looks like. Next slide, please. And then using Open VSPA with advanced scripting technique, we're able to see what each of those points on the solution space determined by the synthesis system. Next slide.
Hello everyone, my name is Louis Garola and I'm the lead propulsion. So our objective was to obtain some database with engine performance and engine parameters. We did this through literature research, case studies, past and present vehicles. Overall, this would provide us with a big, vast engine database. Next slide, please. So when discussing with synthesis and hypersonic convergence, 4 major components came up. Thrust to weight ratio, engine thrust to weight ratio, propellant density, and others. So how does this affect us? We need to look into the weight. Weight is important as it would affect weights and balance, the volume of the vehicle and the geometry, and others. Next slide, please. So overall, when we came to the engine performance and the engine database, some of the parameters we resolved are the table here below, where we obtained the minimum, the maximum, and the median values. These values will be used by synthesis team.
Hello, my name is Ben Tran. I am the lead for weights and balance and structures and materials. And in PS, we were tasked by synthesis in order to calculate hypersonic convergence sizing parameters for the weight budget equation. We did this by conducting research into historical vehicles and assuming some certain weight estimations in order to make calculations more simple. Next slide. We determined the structural index and other parameters from vehicles such as the X-20 Dinosaur, the Space Shuttle Orbiter, the Falcon 9, and the Saturn V. In order to do this, we also made some assumptions. So we made sure that the unmanned vehicle system weight was equivalent to the avionics, the cruise system specific weight was equivalent to equipment weight, and the variable system weight was equivalent to hydraulic and electrical. This made our calculations simpler and made our use of variables over to synthesis. Next slide.
So for parametric sizing for trajectory performance, we have an undefined configuration, and one of the difficulties is using a low fidelity method that lets us have a parametric variable that can be iterated on across different propellants, across different propulsion systems. And so what we settled on was using delta V analysis from certain optimized methods, which combine both empirical and by hand analysis in order to develop weight ratios. And we can go to the next slide.
In trajectory performance, we use methods such as the Walker equation to come up with our weight ratio for the first and second stage. And with those ratios, we get the inputs into the weights and balance, propulsion, and aerodynamics. And with the methods we use it to minimize the gross weight of the vehicle and to maximize the delta V split of the vehicle. Next slide.
So with those results, we iterated over several propulsion and weights and balances figures, and what we ended up realizing was there was a high favorability towards method-logs configurations, and those weight ratios were designated to synthesis so that they could input them and utilize them in the convergence. So we verified our results along the way using Falcon 9, primarily trying to get the code to not only put out accurate results by comparing with open software tools, but also trying to get at the actual solutions of those vehicles in that optimized estimate, and realizing that our configuration is vastly different, so we understand that there is some difference. Next slide.
We took all the inputs from the teams and decided to test it out with the Falcon 9 and the Starship, and our calculations ended up under 10% of error, so we decided to move on to our next step. Then we took four different train matrices to identify the fuel type, the structural index, the payload, and orbital altitude to give with the disciplines, and the teams to hit a certain point which fit perfect for everybody. Next slide. And that gave us a solution space. And from there, we decided to pick a design vehicle that gave us our weight and volume buckets.
And then that takes us into the next stage, which is configuration layout. This is where we lay out the different geometries of the vehicle and test and examine different components and try to examine different arrangements that we can possibly use.
All right, I'm Ian, part of synthesis, and in configuration layout, we want to take the parametric sizing data and turn it into a physical layout. And synthesis role is to make sure that the layout stays consistent with the latest sizing data.
So as Ian just stated, we wanted to use that data. So the propulsion team wanted to figure out what engine we're going to be using, the engine configuration, and of course the propellants. While we're doing so, we were going to be using the engine database created in PS to figure out all this information. Next slide, please. So from the payroll information, the candidates came out to be the BE for the Raptor 3 and the Merlin, with combinations being RP1 and LOX, as well as methane and LOX. Next slide. So the overall engine that we were selecting was the Raptor 3 sea level, as well as the Raptor 3 vacuum. Looking at the slide here, we're able to see the engine data as well as the propellant details. Next slide. Overall, knowing the engine that we'll be using for both first and second stage, the next step was to look at the engine layouts. Looking to see if we want asymmetrical or asymmetrical design and why it's important, as well as engine link input. Slide. Looking here, we're able to see the first and second stage. We used a asymmetrical design due to the fact, as when we were talking stability control due to engine gimbling and engine failure, this design allows for there to be corrections on the way. Next slide, please.
In CL weights and balance, we'll be determining an initial location for these weight components in order to allow for increased performance and stability capabilities, as well as keeping the vehicle reinforced upon re-entry. This will be done by creating a list of historical vehicles, the materials they use, the internal structure, and the layout configurations. Next slide.
Hi.
From PS, the design point will be used. The design point weight estimations will be used in order to calculate a CG, where a low fidelity CG, in order to provide stability control and aero for an initial analysis. Next slide. As you can see, the CG for the first stage is shifting aft due to propellant depletion going towards the engines, which allow for better maneuverability upon descent. And for the CG for the second stage is pushing towards the forward, which allow for better aero and control. Next slide. The inertial tensor was tasked by stability and control over the weights and balance for determining the effectiveness of the RCS thrusters. This was done by simplifying key components into geometric shapes for simple calculations. This was also verified through SolidWorks from the model that was given to us by geometry. Next slide. So windshield development was done by referencing designs from the Space Shuttle Orbiter and other crewed modules. We tried to mirror the successes of the 3-pane configuration for optical clarity and durability. The materials can be seen on the side, and the function of the structure can also be seen. Next slide. For the landing gear configuration, we decided to go with a tricycle configuration, such as seen from the Orbiter and other vehicles. We did this by using side relations and length percentages, and also we will be further analyzing these landing legs locations in stability control in CE. Next slide.
The booster had to be reusable, so we had to put landing gear on it. We ended up looking at the empty weight of our vehicle and decided that the load our vehicle would maintain and counted the legs we needed for each one. We didn't want all the load in 4 legs, so we opted to add more legs to distribute the weight throughout, and we went with the cantilever style legs. Next slide. For the structure of the vehicle, we looked at previous vehicle designs and decided to fit with a certain structural material, structure composite, composition, and TPS thanks to aerodynamics.
Yeah, similar to the first stage, the second stage, we were able to identify key materials and structures and create a list for that. And we found out that the aluminum lithium for its light, weight, and strong material properties, which was ideal for our skin, fuselage, and wings, while titanium is used for the higher load access areas. Next slide.
Hi, my name is Wayne. I'm the lead of the stability control discipline for this project. Our process during the configuration layout phase primarily focused on the selection of control elements to satisfy longitudinal, directional, and lateral stability control. This functions in tandem with our CE process, and we hope to generate solid initial guesses based on multidisciplinary analysis to further our CE progress. Next slide. Our interdisciplinary analysis is largely based on inputs from aero, propulsion, weights and balances, and includes evaluation of the RCS system of the vehicle, and physically justifying the control elements via inputs from the remaining disciplines. Next slide. Our CL process functions in tandem with the CE pipeline. We are making our initial guess of our control configuration based on empirical data, funneling that to CE to evaluate the stability of the vehicle, and then making physically informed design changes following that process. Shown here are some of our initial design considerations when selecting the control elements for the first stage vehicle. This largely consists of structural integrity concerns. Next slide. Shown here are most of our design considerations when working on the second stage of the vehicle. An important mission phase regarding the second stage vehicle includes the reentry, which might provide unfavorable heating on some atmospheric control elements. Next slide. So starting off with our initial control selection, for the first stage includes RCS thrusters. This is a common way to adjust the attitude of the vehicle, and it has been shown in the Falcon 9 and Starship. Next slide. We also are using grid fins for our initial selection. This is a fairly new method of controlling the attitude of vehicles and also decelerating the vehicle on descent. This has been verified with the Falcon 9 and the Sikorsky 12 rockets. Lastly, for the first stage, we're using gimbaled engines to adjust the attitude of the vehicle. This is a very strong battle-tested method of controlling the vehicle and fairly newly actively stabilizing the vehicle via a closed-loop system. This has been verified using the Falcon 9, Saturn V, and Ares 1 vehicles. Moving on to our second stage, our atmosphere control selection initially was ailerons, a V-tail, rotovator, and a body flap to handle longitudinal, lateral, and directional control. This is largely a derivative of the X-37 vehicle. And lastly, for our non-atmospheric control elements, we are choosing RCS thrusters, gimbaled engines for our second stage vehicle for much of the same reasons as the first stage vehicle. Our initial selection of placement and sizing for the atmospheric control elements is a largely empirical process due to there being a lack of information on sizing control elements for hypersonic speed regimes. Shown here is our data for this process. Next slide.
As mentioned by the Tachyon control lead, it was found, we went through the geometric database. It was found that there exists a relationship between the side of the platform area of the side of the fuselage, the platform area of the wing, in relationship to the tail for the initial guess for placement onto the vehicle. This was done by iterating through the vehicles in the geometric database and using an R-squared criteria of 0.7. As you can see, we have the result of our initial guess of what the tail is going to look like on our vehicle. With a height of 5.7 and a tip cut of 3.4, we have what our initial tail looks like over there. Next slide, please. A similar methodology was done for the initial sizing of the engine by using the engine layout produced from the propulsion discipline of 7 engines. The control ratio, which is the ratio of the engine torque to the aerodynamic torque, there was a criteria saying we have to have greater than 1.5 in order for our vehicle to be controllable. And this was done with a maximum deflection angle of 4 degrees and a minimum of 4 engines to gimbal in order to control our vehicle. Next slide.
Similarly, the grid fins were sized using the control ratio and by conducting literature research on vehicles such as the Falcon 9 and the Starship. In order to do so, we were able to define the relationship between the size and the required drag that was produced by each individual grid fins. The location of the grid fins were justified by creating the longest moment arm by producing the small amount of force vector. Next slide.
We chose to size the RCS thrusters from the perspective of passenger safety. So we are using basic force and moment relations to calculate the amount of G-force a passenger will face when the RCS thrusters are active. We're assuming the RCS thrusters are firing in short bursts. So we came up with a maximum RCS thrust of 4 kilonewtons. Shown on the plot is, with space shuttle lives, it's around the same value.
My name is Hussein, and I'm the lead for aerodynamics and configuration layout. We are determined to find the best wing configuration for our vehicle, and it also includes initial research and manual code in order to do that. Next slide.
So one of the significant challenges of aerodynamics is our wing design. And why this is so hard is because we have to deal with completely opposite conflicting requirements. On one hand, we have to perform through extremely high speed regimes, hypersonic speeds up to Mach 25, extreme heating and high thermal loads. And on the other hand, we have to land, which is going to be at extremely low Mach numbers. We're going to be moving really slow with the lower atmosphere. And then on top of that, we also want to not produce any lift during ascent, because as the rocket's ascending vertically, if we're producing lift at a zero angle of attack, then it's going to pull the rocket off course and make it unstable. But at the same time, we need to generate enough lift to land. So this was really challenging, and one of the ways we tackled this was through symmetry. We studied symmetrical airfoils and chose one that balanced the hypersonic versus the subsonic requirements the most, looked at different wing placements, and on that striving for symmetry, we went for the mid-wing configuration, so that way we control the angle of attack and how much lift we have without generating any during ascent. Then finally, we researched every possible wing configuration, eliminated the unfeasible ones, and decided to focus in on swept wings, tapered wings, and delta wings.
The wing placement on the long axis of the body was determined by determining the shock cone angle of the vehicle during the descent phase. Shown on the plot is the range of angle of attack that the vehicle experienced during the ascent. And we're placing the wing further back so it's within those shock cones and not interacting with any shock waves at all. This was verified using real data from the paper that this method was derived from.
So the key task for the geometry team during this configuration layout phase was to shape and size the vehicle with the results received from the parametric sizing phase. Also, we need to integrate both the internal and external components, keeping in mind the iteration that's going on. So it was chosen to use a generic physics-based methodology to know what the wing is going to look like, which is a delta wing, and then also with the fuselage put together. Next slide, please. The methodology chosen was to use a glass-like view to make sure we can physically see what's going on internally and externally, because the external features affect what's going on inside the vehicle. As you can see, this is all multidisciplinary inputs going on, and as said by the chief previously, there are a lot of trade-offs that goes into. We can see the different updates going on for the second stage vehicle. Next slide, please. And the same was also done on the first stage vehicle, where we were constantly updating based on the evaluation results received during the configuration evaluation phase. Next slide.
So when it came to the first stage and second stage landing, we inquired to weights and balance. We overall, the first stage went with a cantilever design, looking at the new Shepherd and new Glen vehicles. To the picture, we're able to see 6 standing legs, and on the bottom right, we're able to see the second stage of the vehicle using a tricycle configuration with a total of 6 wheels. Next slide.
And as such, we have the tau, the Kucherman slenderness parameter from the design point. We have what the vehicle looks like, which is the first stage and the second stage. Next slide, please. And then using these refinements, we have a table that goes into place that takes into account what each dimension of each vehicle looks like, where we're constantly updating during each iterative process. Next slide, please. And then with these, we can understand and make informed decision of what our vehicle looks like alongside all of the previous, past, and present, future vehicles, what they look like. We can also provide all of the disciplines with the database needed in order to make informed decision, like guiding the stability and control team to size the vehicle, the aerodynamics tool to perform aerothermal analysis and see what other vehicles look like during them. Also the propulsion discipline for engine relation. Next slide. And then among
Buran looks like.
Buran? Buran looks closely like the space shuttle. Previous slide.
The image was there before.
Previous slide.
Okay, go back.
Closely like the space shuttle.
Okay.
And then after that, we can see what the wing body KW tau relationship looks like in comparison to the overall, in comparison to the literature research data. We found out that was 10.82%, which is pretty close to literature result, and then which means we're well within range. We do not want to develop a vehicle that's not feasible. Next slide.
All right, so after configuration layout, we have a physical design, and now we want to evaluate this design to make sure it can complete the mission. And so we can do exactly that by taking this layout to the next phase of configuration.
And as the name suggests, that's exactly what we're doing. The goal in this stage is to finalize, verify, and analyze the configuration. And as you can see from the multidisciplinary analysis behind me, this is a very complex and in-depth process, so I'm not going to go through all of that in this presentation because it can be basically boiled down to this. We have these baseline requirements through the mission phases that boil down to specific things that each discipline needs to do, like shielding during re-entry, generating lift, enough thrust. Each of these have a specific requirement that ties to a certain discipline, and our job is to basically deconstruct it and then reconstruct it into a cohesive vehicle architecture. And similarly, another big goal of configuration evaluation is to reconverge. And we're going to do this in a similar way by taking all of our multidisciplinary inputs and combining them into a refined solution space by taking the discrete inputs that we used in parametric sizing and swapping those for functions or relationships that we can use to analyze, scale, and perform feasibility checks of the solution space.
So for trajectory and performance and configuration evaluation, we have a configuration of interest that we now want to analyze its performance through the different flight phases that we already identified all the way back in PI. We do that through a little bit of a higher fidelity estimation. Now that we have a vehicle, we're gonna use 3-degree of freedom simulation through a point mass that exhibits the properties of the vehicle, which come as multidisciplinary inputs. That data is passed to different disciplines. Those disciplines check. They reiterate the configuration if they need, and then we do the same process over and over again until we reach a happy solution. Next. So we have several multidisciplinary inputs which build up our model. There are aerodynamics, weights and balances, geometry, and then as we continue to build the model through different flight phases, we begin to change what flight phase of analysis and slowly build up our efforts. Next slide. Those efforts can be visualized here operationally as a large picture. I would love to go into detail, but to keep things simple, we successfully were able to model our vertical launch all the way to deorbit, with the second stage having plenty of fuel to initiate a Hohmann transfer to the final orbit, and with the first stage booster being able to initiate boost back and landing just as we planned, acknowledging the challenge that we had to iterate not only the vehicle, but the trajectory several times. Next slide. So we can actually visualize those outputs, and they are in the form of Mach number and propellant mass profiles. There was some more. Dynamic pressures we were able to give to. We take all that data from those simulations and we give them to the disciplines that need it. And they use that information for dust vector control sizing, CG analysis, and higher fidelity estimation. Next slide. And along the way, we verified that process with not only external online simulations such as flightclub.io, but also with empirical data that we then analyzed from Falcon 9, Space Shuttle, Starship, and we were able to verify our altitudes and speeds, our performance characteristics, and our trajectory geometry. Next slide.
So when it came to the propulsion, we knew how many engines we were going to be using for the first stage. We knew how many engines we were using for the second stage. All this done was use the empirical data from the database, but now we wanted to do a higher fidelity and check on these numbers and see if these engines really truly accommodated the vehicle and the mission requirements. Next slide. So one of the first things was looking at the propellants, seeing if we have enough fuel in order to meet the mission requirements. Looking at the bottom left, we are able to see how the fuel meets all the requirements. And to the up to the right, we're able to see the performance of the engines. Next slide, please. So we wanted to conduct bigger analysis. We looked into CDA and RPA. With these tools, we looked at certain parameters, which was the chamber pressure, expansion ratio, and of course the oxidizer to fuel ratio. We conducted this analysis for the first stage Raptor engines, and we were able to conclude that we got differences minimum of 6%, which is quite in the range. And we also conducted analysis for the chamber pressure and oxidizer to fuel ratio. And overall, looking at the plus to the right, we can see how they vary, but still, even if they vary due to the small percentage, we still obtain values less than 5%. Next slide.
So with the different engines that we identified and we analyzed in CE, mainly the BE4 and the Raptor 3, we were able to delineate the fact that although there may be a marginal performance gain with the BE4, there is not enough evidence to suggest that installing them on the vehicle would lead to the performance gains that we want. And so we justified that with, due to the nature of the obscure data and the mass consequence that we would have with the BE4, we then gave that data in the form of functions to disciplines like trajectory performance and weights and balances in order so that they could confirm throughout the flight phases the vehicle performs as intended.
Given the design point data, we are now going to determine a higher fidelity weight estimation for all of our components. This will allow us to dive deeper into load analysis and determine how the CG will shift dynamically through the flight stages. Next slide. So we will be using HASA due to its ability to estimate hypersonic vehicle weight components. And it uses historical data and relates this to statistical equations for weight predictions. As you can see, we verified it with the spatial orbiter and the general dynamics orbiter, and having a low percentage error for the structure and the system weight, which we'll be using for our calculations. Next slide, please. So, as you can see, we're using the systems and the structures weight. Propulsion will be assisting us by giving the engine weight, and trajectory will be assisting us by giving the propellant weight over time. The separate structures, such as the grid fins, next slide please, and the body flaps, and also the tanks will be determined from the assistance of geometry and stability and control in order to determine the effectiveness of each control effector, and then with the help of geometry's volume, we will be able to calculate the weight estimation for those. Next slide, please. So we will be using the Falcon 9 in order to verify the CG tracking throughout the mission phases. Next slide. As you can see from our Tachyon vehicle, the CG has been moving in the same manner as the Falcon 9. The CG shifts towards the nose due to the second stage, and at stage separation, the CG will jump towards the second stage. The CG matches pretty closely to what was estimated initially in CL. And next slide, please.
Structures started the analysis and the load analysis for actual load. So we started using the HASA code calculations and started to see where all the weight was going to be and how it affected the entire structure, because we needed a selection for the material to make sure that it can withstand the actual loads. Next slide. The same thing had to be done with bending moments and shearing loads. Shearing loads usually are caused by winds that are flying through and make it, shear itself. So we need to make sure the material can withstand the shearing. If not, we have to change to a different material.
Moving on over to landing gear analysis, the vehicle will be landing at 10% of propellant weight, and we will be determining the landing based on landing forces and the static weights on the rear gear. So as you can see, the displacement on the landing gear is very minimal, therefore the landing gear is providing an adequate amount of structural support for the second stage vehicle. Next slide. We can, from these structural analysis for the first stage, it can be seen that cylindrical support with aluminum 2219 and 7075 can be used in order to mesh a better material compatibility for the first stage. Next slide, please. And for the second stage, it can be seen that we're using aluminum lithium for its lightweight and durable capabilities, and also titanium for those critical areas. Some future research that we need to dive into is our first and second stage structural landing analysis, as well as our landing leg analysis. Next slide, please.
For geometry in the configuration evaluation phase, the major task was to further refine our vehicle and also output a 3D model. But in doing so, we need to pay attention to the mission requirement, which was the human capability. So we need to make sure the human seating position and also develop reclining chairs to make sure we can accommodate the high G-force during ascent and also re-entry flight phases. Next slide, please. Also, another key factor after obtaining the maximum load from the weight and balance discipline, we need to determine the maximum turn angle on our vehicle in order to make sure our vehicle can also turn in a proper manner, and also the forces on the main gear and the nose gear that's going. So we ended up determining that it's going to be between 80 to 90% the main gear forces that's going to be on the vehicle load, and also the nose gear is going to carry no less than 5%. That's by doing such, the vehicle can actually turn about its position. Next slide, please. Also, we can further optimize our vehicle by looking at each component, such as the wings, the fuselage. We can try to reduce the wave drag produced on the fuselage, and also develop simple cross-section that's easier to be manufacturable. Next slide, please. Finally, we can develop simulation results that help us to look at what the claims by other disciplines, such as the flight phases, the landing angle of attack, the rudder deflection, and so on. And during this procedure, it became evident that the more we further optimized our vehicle, it looked good and it performed better. And with that being said, the saying, if it looks good, it flies good, actually became evident. Next slide.
For aerodynamic storm, our objective in CE is to evaluate each flight phase of our vehicle to make sure it can complete all mission requirements for our missions. Then we also found our heat function and heat distributions for our vehicle. Next slide.
So as previously mentioned, designing the wing is extremely difficult because of all the requirements that oppose each other and are the complete opposite. So the best way to do this, to have a fully defined geometry that completely covers all mission phases, is to write a MATLAB code which iterates through every single wing geometry and outputs the resultant lift that's generated from it and other performance metrics, and then also outputs a plot which visualizes the wing. So this is the history of how we did it. The first design point didn't have enough wing area, so we had to choose a new design point. The second one had sharp tips that would have burned on re-entry and melted off, so we went with a tapered wing. The tapered wing had enough lift, but wasn't compatible with the control surfaces. So finally, we made the one you see, that's the delta wing, that has a flat trailing edge and doesn't have the sharp wing tips. And then with the remaining planeform area, we used strakes to generate vortex lift. And that was the final wing that was produced.
The methods that we use to calculate heat flux and the heat distribution and the aerodynamic forces are basically L and .com for vehicle. We verify these methods using spatial data and multivariate data that were found online. And then for the here are like the graphs that we found for our vehicle, and we found that we use these to find the forces on all models at angle text from -5 to 20. Next slide.
Shown here is the lift coefficients versus angle of attack for every second stage mission phase. It's important to note that during the high angle attack during reentry, the vehicle doesn't stall. Here's our L over D graphs for all of our second stage mission phases as well. This demonstrates that our vehicle is a low L over D glider, similar to Space Shuttle X-37. Our objectives for S&C during the configuration evaluation phase is to evaluate our initial guess, determined in CL, evaluate stability of it during all flight phases, and then generate new vehicle configurations depending on those results. Next slide. We verify this with other simulations for the non-atmospheric control elements, and here again shows our pipeline between CL and CE. We also assess critical mission phases such as landing and the glide descent phases. Next slide. Here are our inputs and outputs. We are outputting the further refined RCS data to the propulsion team, along with our final vehicle configuration to geometry and weights and balances. Shown here is our process using usafdigital.com, shown by DigDat. We evaluate the static stability for longitudinal, lateral, and directional stability axes for all mission phases. Shown here is our first and last evaluation. We had around 4 or 5 iterations of this evaluation, after which we made informed design decisions for each vehicle configuration. Started with VTail, it provided us more issues than positives, so we eventually moved over to a vertical tail, and with this, our vehicle was fully statically stable. Here's some of our stability analyses for the landing phase. Next slide. We also verified this with the Space Shuttle Orbiter. We received a minimum error of less than 1%, which is pretty good.
So trim state for the first stage descent was done in order to determine if the vehicle was able to basically glide down safely, and it can be seen that the residual total moment is low enough for the vehicle to descend safely, which verifies the vehicle's capability of staying within trim upon descent. Next slide.
In doing so, we developed a control system where we can verify the engine gimbal condition. Next slide, please. That way, we can make sure our vehicle during ascent phase is stable with any aerodynamic force that's coming unwanted. Next slide.
The RCS was also analyzed. We developed a closed-loop bang-bang closed-loop stabilization system. This is used on similar vehicles like the Ares 1, Space Shuttle, Falcon 9. Here shows our activation times for the RCS system, which is outputs the propulsion discipline. We also analyzed the landing trim. Using OpenVSP, we deflected the body flap and elevons to trim the vehicle at landing at an angle of attack of 13 degrees.
Alright, so on the later cost and market, and finally, we want to estimate the development, production, and per flight cost of our vehicle. So we need a cost model that is accessible and requires minimal input. So next slide. Me and Ben went through several options and ultimately ended up with trans cost, which claims to estimate cost within a 20% margin of error. And it provides cost estimation relationships for many different vehicle types and propulsion system types. And as you can see on the right, there are plenty of equations to use for our vehicle.
So trans cost was verified by using historical vehicles such as the Falcon 9 Block 5 and the Space Shuttle Orbiter. And you can see that for the development, production, and the cost per flight values, that the average between the estimation cost is way below the expected maximum percentage, which means that the trans cost method can be used to estimate our vehicle's cost. Next slide.
And we can do exactly that by taking the required inputs from the relevant disciplines, and it resulted in a development cost of $3.7 billion, production cost of $630 million, and a per flight cost of $261 million. We can compare that with the Space Shuttle, which had around $50,000 per kilogram to payload to orbit, and compare that to ours, it's less than $9,000.
So as previously mentioned, one of the main goals of configuration evaluation is reconvergence. So right here we have our starting point. We have a refined solution space where we updated a few parameters based on design inputs, and then also added a cost function so we can evaluate the price of each design point. But our main goal will be to finally reconverge by taking all disciplines and having them develop MATLAB functions that will perform feasibility and risk tests for every single design point and use that to reconverge on a better vehicle. Finally, the conclusions, the takeaways in this is that our vehicle has been very well fully reconfigured and verified, and most of the major issues and trade-offs have been resolved. Our next step will be reconvergence, and we're expecting to have that done next week. Thank you all very much. I appreciate your time.